When we think through what's happening inside of a pH probe, though, we should probably know a little bit about what's happening on the glass. So on the inside of our glass membrane, we're going to have our internal solution that's going to have an activity of 0.1. Remember that, crudely speaking, that means the molarity is 0.1 molar, but with activity we don't say molarity, and we're being a lot more specific because we're using activity coefficients. Now, we're going to have a hydrated gel layer here. And in that gel, there's actually going to be the ability for H plus or even sodium ion to end up sticking inside of this hydrated gel layer. But it's a pretty thin layer, talking 10 nanometers. So it's not going to be able to have a whole lot bind in there. On the other side, we're going to have another hydrated gel layer, and this is going to be on the inside layer of our probe, outside layer of our probe, the external solution. We're going to have a variable amount of H plus. Remember, we always say that a pH probe is really measuring activity, not concentration, but with some knowledge about activity coefficients, we get our concentration, and often we just say, they're about the same thing. So in that thin layer, we're going to have H plus sticking on as well. Now you can picture that if we have a certain amount of H plus sticking here, it's going to have a certain amount of plus charge. Depending on how much plus charge we have sticking in here, that's going to dictate where all of these ions inside of the glass are going to go. Now usually we think of glass as just being a solid, and we don't think of things migrating through it. But within a glass, we actually have our oxygen and silicon structure. You can see that it's going to have this nice winding kind of pathway throughout. And I also want to emphasize the same thing they're bringing up down here in the blurb. We're having to look at this in 2 dimensions. But remember, this is going to be a very complicated 3-dimensional lattice of silicon dioxide, or actually silicon tetraoxide when we think through the individual network on each of these. So we're going to have a big 3-dimensional structure with all these areas that are porous. And inside of those pores, we can have different cations. So we'll have cations like lithium, sodium, potassium, and calcium that are coordinating with our oxygen atoms in there. And remember, each of those oxygens will have the lone pair of electrons times 2. So those 2 pairs are different spots for these to bind on, just using ion-dipole interactions. Okay, now, when we think about that, we can say, oh, okay, so what you're really saying is we've got a bunch of these cations that are dissolved in this glass. Same as before, what we were talking about. If we have lots of positive charge on this side, those cations are going to kind of migrate the other direction. And so we're going to end up having a junction potential form. So by measuring the junction potential across that glass membrane, we're able to determine the pH on each side. And so we would just determine our voltage, and by using an equation we can convert from that voltage into pH, which we can then convert into activity or H plus concentration.